Welcome back to the Quantum Rings Quantum Summer School. Today is the final episode of the series. Thank you so much for following along to this point. I've had such a great time teaching this series, and today we're going to be doing something really fun, which is a capstone. We're going to be running QAOA with 100 qubits. Let's do it. So for today, we're going to start off with a quick recap of the whole course. Then we're going to move over to the coding notebook and we're going to do a small example of QAOA, which is actually very similar to what we did in episode 12. So that's just recap again. And then we're going to be taking that to the next level and doing QAOA with 100 qubits. And then finally, we'll wrap up and talk about the road ahead. So the first thing I want to say is congrats, you made it to the end of the course. Hopefully you learned something. The goal of this course was just to provide an introduction to the field and exposure to a lot of topics. So we were going for breadth rather than depth. So the point was not necessarily to become an expert or master the subject matter, but more so to just get some exposure to the field and build a foundation so that you can go on and learn things on your own or take more advanced courses. So I have seen this material dozens of times and I've worked in this field for many years and I'm still learning all the time. So if it didn't make perfect sense to you the first time around, that is totally okay. This is just meant to be a first introduction and provide you with the background so that the field is more accessible to you and you can continue to learn. And we covered a ton in this course. We had 14 episodes, including this one, and we started from ground zero. So this course had no prerequisites. So the very first thing we did was talk about the math that we needed to know in order to move forward and also setting up the SDK for quantum rings. In that one, we mostly focused on linear algebra and then also quantum mechanics notation. So we learned about bras and kets and operators, expectation values, inner and outer products. And then we set up quantum rings. In episode 2, we talked about single qubit gates and how they're simply rotations on the Bloch sphere. We learned about quantum superposition and how measurement collapses our wave function, it collapses our superposition. And even though we exist in a superposition state at first, after the measurement, we'll only end up in 0 or 1. And then we also learned the BB84 quantum key distribution protocol. So this is the quantum solution to the key distribution problem, and we can have two people build up private shared key. It's basically guaranteed by the laws of quantum mechanics that their key is safe from eavesdroppers. Then we talked about entanglement and multi-qubit gates. So we learned how to express multi-qubit states in both vector and ket notation. We talked about the C0 gate and how we create entanglement with Hadamard and C0 gate. And we also talked about quantum teleportation, where you can teleport a quantum state as long as the person you're teleporting the quantum state to, you already share an entangled pair with them. Then we talked about circuit composition and control flow. We covered classical and quantum logic. We learned how to decompose gates into other simpler gates. And we also talked about universal gate sets. So we know that we can break down any circuit into some base set of gates that covers everything. In episode 5, we talked about two major building blocks of quantum algorithms. One of them is oracles, and the other one is amplitude amplification or diffusion. So we talked about both phase flip and addition oracles, and we also learned how amplitude amplification works, where we flip all the amplitudes over the mean or the average amplitude. In episode 6, we covered toy algorithms. We learned 3 ones. The Deutsch-Joscha algorithm, we're trying to determine if a function f is constant or balanced. For Bernstein-Vazirani, we have some hidden string s that we're trying to find. And we are only given the function x.s mod 2. And then you have to figure out what s is. And then Simon's algorithm is the first kind of period finding thing that we did, where you have some periodic function and you're trying to find the period of it. And this one kind of served as kind of inspiration for Shor's algorithm, which we learned later on. Then we talked about Grover's search algorithm. So we combined that phase flip oracle and amplitude amplification in order to basically amplify the the correct thing that we're searching for and give us the highest possible probability of measuring it. Then in episode 8, we talked about both the classical and then the quantum Fourier transform, and we constructed the quantum phase estimation algorithm. So basically finding the periodicity in the amplitude of quantum states. And then for Shor's algorithm, in episode 9, we first talked about RSA key encryption and why Shor's algorithm is a threat to that. And then we talked about quantum order finding, and finally performed Shor's algorithm for some simple examples of like 15 equals 3 times 5. We also talked about noise and error mitigation. Up until that point, everything had been perfect and ideal, but in real life, our qubits are noisy, prone to error, they decohere. So we talked about the two arguably most promising platforms for quantum computing, neutral atoms and superconducting qubits. We talked about qubit decoherence and other error channels like state preparation and measurement errors. And we talked about some error mitigation techniques like dynamical decoupling and zero noise extrapolation. In episode 11, we learned our first variational quantum algorithm, which was VQE. We talked about Hamiltonians and ground states, and we covered the structure of variational algorithms in general. And we also performed VQE for an electron in a magnetic field and an H2 molecule. Then we learned our second variational quantum algorithm, which is QAOA. We compared VQE and QAOA and when to use VQE and when to use QAOA. VQE is good for things like finding the ground state of a molecule, and QAOA is good for things like finding the optimal solution of a combinatorial problem. And we also learned how to design cost functions, cost Hamiltonians for QAOA, and prepare the QAOA ansatz and perform the optimization loop. Finally, in episode 13, we talked about quantum error correction. So this goes above and beyond error mitigation, where we're taking a bunch of physical qubits and encoding them into a logical qubit. So we first covered classical error correction, and then we learned a couple different quantum error correcting codes, including the 3-qubit bit and phase flip repetition codes, the 9-qubit Shor code, which can correct any single qubit Pauli error. And we also learned about surface codes. So now let's move over to the coding notebook, and we're gonna do a large scale example of QAOA with 100 qubits. And we can call this utility scale because already with 100 qubits, we can do a combinatorial optimization problem for a graph with 100 nodes. Let's do it. So first, import all the libraries that we need. And then we have a bunch of helper functions here. One of them is plotting the parameter evolution. So we're calling QAOA, we're looking for the vectors gamma and beta, which parameterize the ansatz. And so this is just when we're optimizing, we can keep track of the gamma and beta values and plot their values for each optimization iteration. Here is just to convert integers to binary strings. This is for at the very end, when we've done our QAOA algorithm, we found our best choice bit string, and then we're gonna plot the result of the best partition. And then these two I'm going to talk about later, but just in case you want to skip over part 1 and go straight to part 2 with the 100 qubits, you'll need those two functions. So quick recap of how QAOA works. QAOA is just a very specific case of VQE. We're trying to minimize the expectation value of a Hamiltonian, but the Hamiltonian that we're working with is very specific. So basically, the types of Hamiltonians that we're going to be working with are linear combinations of products of sigma z. So we can have terms like sigma z1 times sigma z2 with identities on all the other qubits, and basically linear combinations of terms like that. This turns out to be very good for combinatorial problems because you can very easily map problems that relate to, for instance, partitioning the nodes in a graph into two sets onto this framework, because you can say, okay, I'm going to select a certain number of nodes, and that's one group, and then the ones that are not selected are the rest. The ones that are selected are 1, labeled with 1, and the ones that are not selected are labeled with 0. And that's exactly what we're doing in the max cut problem. So the max cut problem is the following. We have some graph G. It has vertices and edges. You can also call the vertices nodes. I use those interchangeably. And we want to split G into 2 sets, so we're selecting some subset of vertices. And then we're going to cut every edge which connects 2 vertices in different sets. And for max cut, we want to know the partition of G, which maximizes the number of cut edges. So there's classical function, which you would want to minimize for this. Basically, if you have 2 vertices, I and j, which are connected by an edge, if they're both in the same state, either 0 or 1, then the function is going to equal 0. But if they're in different states, then the function is going to equal -1. And so minimizing this is going to give us our max cut because we're rewarded for cutting edges between vertices that are in different sets. So we just translate that to something that our quantum computer can understand. And we use terms that are like sigma z on qubit I times sigma z on qubit j, because it has this same structure where if they're in the same state, the energy is positive, and if they're in different states, the energy is negative. That's the way that we can encode this into a cost Hamiltonian, where our goal is to minimize the energy. The minimal energy state is going to have the max cut. So QAOA works by using that cost Hamiltonian and applying a cost unitary built from this Hamiltonian and a mixing unitary. So basically the cost Hamiltonian is z rotations, but we know that in our quantum state, every time we perform a z rotation, and I never remember which is longitude and which is latitude, but the angle down from the z-axis, which I think is the latitude, doesn't change. So your probability of measuring 0 or 1 is unchanged. So we're going to use our mixing unitary, which has sigma x's in it, and that's going to rotate us into the x basis and turn those phase changes into changes of measurements in 0 and 1. So let's do this first with 5 qubits. This is very similar to what we did in episode 12. We can have a graph with 5 edges, and I think this drew it in like the least clear way possible. Okay, that's better. Just looking at this, we can think about what the max cut should be. If we can see that there's a lot of edges coming out of vertice 2. So 2 goes to 3, 0, and 1. So if we put 2 in a separate set from 3, 0, and 1, that's going to lead us to cutting 3 edges. That's pretty good. And then if we put 4 in a different set than 3 and 0, then we can cut 2 more edges. And there's only 6 edges total, and this turns out to be the best possible solution. So the max cut should be 5, and we can recover this with QAOA. So the first thing that we need to do is define our cost Hamiltonian. And the way that we do this is with these Pauli lists. So basically anywhere where you want, you can put a z for sigma z at any location in the string, and then i's everywhere else. So for instance, if you did like z, z, I, that would be a term sigma z on qubit 1, sigma z on qubit 2, and identity on the rest. So here's what our cost function Hamiltonian would look like. We just have every edge in the graph has a term associated with it. So this term is for the edge that goes between the first qubit and the last qubit. Then we can make our QAOA ansatz. We can just use this built-in function from Qiskit to make it super easy. We plug in our cost Hamiltonian. The reps is the number of layers that we want. So basically we're going to do our cost unitary with parameter gamma 0, and then our mixing unitary with parameter beta 0, and then cost with gamma 0, and then mixing with beta 1. Those are 2 layers. And we can see the circuit parameters here are gammas and betas. The reason that this is nice is because we can use this circuit and just, instead of reinitializing the circuit every time, we can just update its parameters. And that makes it really easy to do an optimization loop. Then we need to create our backend. We have to transpile it, and then we can see what it looks like. So basically, we're breaking down the QAOA ansatz into some simpler set of gates. Then we're going to execute the circuit. So we have to pick some initial parameters. So we just randomly pick some gammas and betas to guess. You could change these up if you're interested. For this one, we're going to want to use the estimator for the backend. And that's because we want to get the expectation value of the cost Hamiltonian. And the estimator, that's pretty much exactly what it does. So that's what we're going to use. And we want to keep track of our parameter history over the course of the optimization. And then also the function evaluations. So basically the cost we're measuring as we go along, this expectation value of h. And we'll also keep track of the number of evaluations and how long it took. So here's where we're determining the cost. So we're gonna get our Hamiltonian and apply the layout of the ansatz. And we're gonna run this using the estimator. And at the end, the cost is gonna be from the results object .data.evs for eigenvalues. So our eigenvalue is gonna be our eigenenergy in this case, because we're considering our cost Hamiltonian. And then we're going to keep track of our parameter values and the cost over each iteration. So let's see. We're going to do this. We're going to use our estimator. There's some error suppression / mitigation options that you can use. We talked about dynamical decoupling in episode 10, I believe. So that's what's happening here. And then we can minimize. This is just SciPy optimize, minimize, using our cost function, our initial guess parameters, our transpiled circuit, our cost Hamiltonian that we want to find the expectation value of, and our estimator. Okay. This is going to take a few seconds. Okay. So we can see it took around 60 iterations, and at first it's jumping around a lot, but then our parameters converge very nicely. We can also see what happened with the cost. And here we can see it started off at 0 and it bounced around a lot, but eventually it got lower and lower until it converged on some value. So that's a good sign. And now we can get the optimal parameters for the circuit from our result object. So it's going to just be result.x. And we can assign those parameters to our QAOA ansatz circuit. So here we're literally just plugging in the correct gamma and beta values that we found from our optimizer. And now here we want to use the sampler and not the estimator. So the sampler is going to tell us the sampler is going to give us the probability distribution of bit string measurements, which correspond to the optimal cut of the graph. So we don't want to know the expectation value of anything. We just want to know the probability distribution of measurement results. So let's do that. Okay. And here we can see there's certain outcomes which are more likely than others. That's a good sign because we know that there should only be a few ways of making the best max cut. So now we want to post-process this and see what it actually looks like, because it just looks like a jumble of numbers to me. So we want to get the most likely bit string. So we're just going to look here and find which one occurred the most often. It should be this one here, which is like 01001. Let's see. Okay, but Qiskit does reverse bit ordering, so we flip it back at the end. Just keep that in mind. And then we're going to find the top 4 values. So in this case, it should be these 4 here that are the tallest peaks. And we're just going to plot that. So here's the 4 most likely values. It just makes sense. And we can visualize the best cut on our graph. So here we can plot the result with the most likely bit string, and it will just show the partition. So this is really good because this is what we talked about before we even started this. What should the best cut be? And we said it was the 2 opposite corners of the square. We can also calculate the value of the cut. So here, this is just computing for every edge in the list. If the two edges are the same as each other, it's 0, and if the two edges are different from each other, it's 1. And just summing over all the edges, and the value of the cut is 5. Okay, so now we're going to move on to do something that's actually cool. If you thought that this was perhaps too silly of an example, and we already did it before in episode 12. So now let's do it with 100 qubits. This is a utility scale problem because you can actually potentially solve useful combinatorial problems for graphs with 100 vertices. So yeah, just some examples of things that are combinatorial problems that could be good for QAOA is things like vehicle routing or like traffic management, optimizing schedules, portfolio optimization, and finance, these type of things. So let's make a new graph which has a ton of edges in it. So our graph has 100 nodes and 112 edges. This is what it looks like. And all the steps we're going to do here are exactly the same as we did with the 5-qubit example, just on another scale. So we're still going to have to build our Paulis, but now these strings are going to be 100 letters long. But you can still see here that every term still has only 2 z's in it. And that corresponds to an edge in the graph. So we're going to do one QAOA layer. We're going to pick our initial beta, initial gamma, and then we're just going to set the maximum number of iterations to 100. We're going to make our QAOA ansatz using our cost Hamiltonian with p repetitions. And then we can transpile our circuit. So now, again, we're just going to run that optimization loop. We're going to keep track of our cost, our gamma and beta, and also the amount of time that each evaluation takes. Here's our cost function estimator, which is very similar to in the previous section. We're still just grabbing that eigenvalue, which is the eigenenergy of the cost Hamiltonian. And now we can run the optimizer. This is going to take a hot second, so I'm going to come back in like 10 minutes when this is done. Okay, great news. Our optimization terminated successfully. Took around 43 evaluations, and we got down to costs of around -3.1. So now we can take those optimal parameters that we just found and assign them to our ansatz circuit. And then we can use our sampler again to execute the circuit and then sample from the distribution. This will take us a bit again, just because there's so many qubits. Okay, and the last thing that we need to do is post-process this and get the output result. So let's see our cost over our iterations. It bounced around a lot and then it converged around like -3. And we can also see the parameter history. So we only had one layer, so here's our gamma and beta, what they converged to. And then we want to extract the solution that corresponds to the lowest cost. Yeah. Before we do that, we can also look at how long it took. So we can look at the cumulative elapsed time, and also you can see how much it jumps up by each iteration. And so this took around 25 minutes. We can look at the time per evaluation, so it's averaging around 40 seconds per iteration of our optimizer. And then we want to find out what the best solution is. So all this is doing is just computing the expectation value of the cost Hamiltonian for each of the measured bit strings. And then it's gonna loop through the distribution of results, computing the cost, and then it's going to find whatever one had the lowest cost. So here's our result. And this is not necessarily meaningful, so let's visualize this on our graph. Okay, so something that we can notice right off the bat here is if you look down, for instance, in the lower right part of the graph, where there's like a little U shape, basically, you can see that it alternates like purple, gray, purple, gray, purple, purple, gray, purple. But so it's not perfect, but it's alternating a lot. So you can see there's many places where a purple neighbor is a gray, and a lot less places where purple neighbor's purple or gray neighbor's gray. So this looks, visually it looks okay. So let's see the cut value. The value of the cut is 96, and there was 112 edges in the graph. So we only didn't cut 14 edges. So this may not be the perfect max cut, but this is definitely an approximate solution, and it should be close to whatever the max cut actually is. And then these were our final parameters for gamma and beta. We can also plot the cumulative distribution function. So I'm not going to talk too much about that, but let's just take a look at the plot. But basically on the x-axis here, we have the objective function values. So this is the expectation value of the cost Hamiltonian. And then we have the cumulative distribution function. So basically this wide curve here, the fact that it's kind of tall and flat near -80 tells us that there's a lot of results that had like pretty low objective function values, and not a lot of measured results that had higher objective function values in the range like -50 to -20. So this tells us that there's a lot of candidate solutions that are pretty equivalently good. It wasn't like there was only one or two choices, like which vertices to select, that would give us a really low expectation value. There's a lot of good choices, basically. So there's a lot more to explore here. One thing you can do is try more layers. So you can try 2-3 layers. How does it change? To make this a little less computationally intensive, you can also take a subgraph of the graph we made. So here's an example of how to do that if you wanted to take only up to 30 vertices. And then also in episode 12, we learned about minimum vertex cover. So you can try and implement that for a really large graph. I would also encourage you to think about real life examples where you could use QAOA, and can you make a graph and cost Hamiltonian to describe that problem and then run it. So now let's talk about the road ahead. Basically, the main takeaway I would want you to have is that a lot of progress has been made in the field, and there's also a lot of progress to be made. This is a relatively young field, which means that now is a really exciting time to start learning about it. There's tons of active areas of research. I'm just going to list a couple, but this is not even scratching the surface. Designing qubits with higher coherence times. We know that decoherence is a huge problem. We want to have fault-tolerant quantum computers at some point, hopefully in the near future. And we're going to use quantum error correction to do that. But quantum error correction, as we saw in episode 13, only works well if your physical error is beneath a certain threshold. So we also have to make our physical qubits better. We want higher fidelity single and 2-qubit gates. There's a lot of research on that. Of course, quantum error correction is super popular at the moment. There's also a lot of work to be done in theory still, coming up with new algorithms and new protocols. There's also quantum simulation, so using a quantum computer as a computational tool for simulating physics, like collections of atoms and molecules. There's both digital and analog versions of this, and this is actually the area that I do my research in. Digital just means you're doing the simulation using a bunch of gates, and analog means you're doing the the simulation by making the effective Hamiltonian of the quantum computer the same as the system of interest. So actually this is kind of similar to like QAOA versus VQE in my opinion. There's also a lot of work on scaling up device sizes. We want quantum computers with way more qubits. And this is mainly an industry effort. So there's a lot of work in quantum computing in industry, in academia, national labs. In academia, there's a lot less resources than in industry. So academia is maybe more on the creative side of things, whereas industry is using more like tried and true qubits and methods and trying to make them bigger. There's also a lot of work in designing quantum interconnects. So one thing that we want to think about is, can we convert quantum information from light to a superconducting qubit or from a superconducting qubit to a neutral atom? We also want to think about, if we had two separate quantum computers or quantum modules, like how can we connect them together in order for them to communicate? And there's so many more. Where will we hopefully see quantum computing making an impact? So one is quantum chemistry. This is where quantum simulation would be super useful. It's basically just another computational tool that you could use beyond a classical computer that has quantum properties already built into it. Fundamental physics research, again, from that quantum simulation tool. Finance, portfolio optimization and such. This is where our variational quantum algorithms would be really useful. Also for logistics like schedule planning or route optimization. There's also potential for there to be quantum machine learning. That's an emerging field as well. Material science, again with quantum simulation, and the pharmaceutical industry, potentially designing new medicines. And I'm sure there's also going to be a ton of things that we haven't even thought of yet. As a comparison, I would say the GPU was originally made for like processing graphics, but then after that technology was already made, people realized that it could be really good for parallelizing computation. Now GPUs are a super important tool in regular classical computing. And so I also anticipate similar things will happen here, where once the technology is made, more use cases are going to arise. That's it for this course. I just want to thank you once again for following along. This has been so much fun. If you followed along in the notebooks throughout the course, then you can expect to receive a certificate. A lot of the circuits in the notebooks had names associated with them, so we can see, based on your quantum rings account, which named circuits you have run, and that's how we're going to determine certificate eligibility. So expect a follow-up soon about that. And then also Quantum Rings is going to be having more courses in the future on more advanced topics, so definitely stay tuned for that. Thank you so much again, and that's it.